Hi, everyone. Welcome to week 12 track. Can you hear me? Thanks, Lincoln. Okay, two things. I put last week's completed notebook on GitHub. I'm not sure if you have seen it, but please refer to it because that would be useful for your assignment, which is due soon. Okay. The second point is I'll be going through some of the questions this week on the shared Prac12 handout, which is the concepts explained would be useful also for your assignment, the next assignment. Okay. Before I move on, is there any question from last week's practical? Any questions? No? Okay, let me share the questions. Can you guys download the notebook, please? All right. These questions are from the last two chapters of your reading materials, which is about integration and computing gradients, okay, and especially the gradient descent method. Okay, so you should be familiar with chapters 9 and 10. And like the first question is about Rayleigh distribution. You could have a look at the basic concepts of Rayleigh distribution on the link given, which is from Wikipedia. Okay, it is in probability and statistic, it is commonly used and it's a continuous probability distribution where the support is non-negative values, real values. And the notation is given here like with parameter sigma, where sigma is positive and it is the shape parameter. And the PDF, which is the probability density function of the Rayleigh distribution, is given by x over sigma squared times e to the power minus x squared divided by 2 sigma squared. Here, x is bigger than or equal to 0, sigma is positive always. Okay, first question I've asked is plot the PDF of x for given values. Using last week's code, can you do this? Mathematica has inbuilt function for Rayleigh distribution. You can either use the inbuilt function or you can use the PDF expression. How does it look like? For example, for when it's sigma is 0.5, how does it look like? Anyone? Has anyone plotted it? Okay, let's use the code that we have used last week. Okay, I only changed the name of the distribution and the parameter. Okay, this is similar to what we did last week. And let's have a look at this. Okay, so when sigma is 0. This is the PDF, plot of the PDF. When sigma is 0.5, its peak is around 0.5, and then it's increasing and decreasing. When sigma is 1, the peak is about 1 at 1, and then it's like increasing and then decreasing. It's like a normal, it's skewed normal density function. Okay, skewed to the right. But when sigma is getting high, it's getting more flat. All right. Now using the expression for the PDF, could you show that the cumulative distribution function, which is the CDF of x, is given by this part here when x is bigger than or equal to 0, and it should be 0 otherwise. Remember that fx is the CDF is computed using, say, CDF of x is equal to the probability of x less than or equal to a given value x, which is computed using the integrals. Okay, integral of your PDF from 0 to the value of x. Okay. Okay, you should be able to compute this by hand, but I have given here using Mathematica code what you should be getting. So if you use Mathematica, you could code it like this: integrate fx from x between 0 to u. Here I said u, but that doesn't really matter. So you get this expression. Would you be able to derive this by hand using integration? What would be the bounds on the integral? Anyone? Can you guys hear me? I'm not getting any response. Can you hear me? Oh, okay, good. So how would you proceed to compute the CDF? I've started it. So it's the integral of your PDF. Okay. Let me show this. Okay, let me take a clean page so that we can do this. So the CDF, which is f of x, is the probability of x less than or equal to a given value, which is equal to you take the integral of your f of x PDF dt from t equals 0 to x, which is 0x. Remember, this is t equals 0 to x of your PDF sigma squared e power minus x squared 2 sigma squared. All right, with respect to t. Okay. How would you proceed to find this integral? Anyone? What would be your first step? What type of integrations have you covered? Okay, someone needs to tell me the answer to progress. What would be your first step? Okay, how about you start with substitution? Okay, let's say u equals squared 2 sigma squared, and then take du by dt equals 2x 2 sigma squared, which is x over sigma squared. So you get dt is du. Okay, then substitute in that, you should be able to get 0 to x. X is u. Sorry, I think I made a mistake here. Du by dx. Okay. Let me check this, whether this is what I did. Yeah. So I said, oh, my original one was wrong. This should be t squared. Okay, so I let u equals t squared over 2 sigma squared, which means du by dt is 2t, 2 sigma squared, and then get what is dt, and sub in this part over here, we get only e to the power minus u, which when you integrate is minus e to the power minus u. So that gave us, substituting back what is u, we get e to the power minus x squared divided by 2 sigma squared for when x is positive. Okay. So that's the CDF. Okay, so we just substitute. That would be t squared. Okay. Okay, is that clear? Any questions? Do you have any questions with that part? The next question I've asked is about the show that fx, that is the PDF, is a valid probability density function, which means by showing that the integral over 0 to infinity is 1. Okay, how would you show that? In the next question, okay, that means you got to show that the integral of your PDF over the entire region of its defined region is 1. Okay, how do we do that? Again, you would use you would use a limit in this case, because we know that let's say if this is the upper bound is y, in this case is from 0 to y, x divided by sigma squared. This part is the PDF. This is f of x and dx. From our first part, we know that from 0 to y, if you integrate the PDF, that's the CDF. Okay, that this is the CDF. So plugging in that expression and taking the limit as y goes to infinity, we get 1 minus 0, which is 1. So that shows that the PDF is a proper probability distribution. Okay, is that clear? Any question? You can use Mathematica to check this as well. Okay, in this case, you can use the integrate function of Mathematica. I've defined a function previously, that is the PDF, and take the integration from 0 to infinity, assume that sigma is positive. Okay, and then if you evaluate that, you get 1 here. Okay, so that's the way to check your integration, but in your assignment, you should be doing hand calculation. Okay. You could also do this integration using the Riemann sum, which is the using the n integrate. That's n integrate gives an approximate integral value using the Riemann sum, which is you could check the help function, numerical approximation to the integral. So that's also one. Okay, so these are things that you should be you should be trying before you actually do the hand calculation, just to make sure that you get the right answer. Okay. The next question I've asked is show that the mean of the x, this should be sigma, is sigma times square root of pi over 2. Remember, you get mean equals mu of x. From last week, I've explained that this is equal to you integrate fx Okay. This is what we did last week. So to get the mean of x, which is also called the expected value of x, you would multiply x by the x with the PDF again, and then compute the integration. In this case, your bound is from 0 to infinity. Okay, how would you do that? What's the method that you would be using? This is equal to instead of x. Okay, how would you evaluate that integral? She says, yeah, by parts. Very good. Yeah, you can use by parts here. You could use by parts, or you could use gamma, like I've used substitution. All right, let me show you. By parts should also work. Okay, that's where I started with. And this part is the PDF. That's f of x. And then I've said let t be x squared divided by 2 sigma squared, and then I get dx is sigma squared dt over x. Substituting that here, substituting that for dx, I've got only this part, okay, from here to here, which is e to the power t times square root of 2 sigma squared t, which I could write it as, because 2 sigma squared is a constant, so I took it out, and then I only have t to the power, that is square root of t, which is t to the power half. And using the property of, you could use by parts also, okay, but using the property, because I'm more familiar with gamma function, I've used a property of gamma function. So in general, gamma function is given by this integral here, where it's t integral from 0 to infinity t to the power x minus 1 e to the power minus t. So we got almost up to that. Here we need to rearrange that t to the power half in this form. So I've said t to the power half. A half is 3 over 2 minus 1. So the x is 3 over 2 in our case. The other property of gamma function is that we can say it's gamma x plus 1 is x times gamma x, and gamma half is square root of pi. So using these two properties, I could simplify this integral. So this is gamma 3 over 2 from here. Okay. And gamma 3 over 2, I can write it as gamma 3 over 2 is equal to gamma half plus 1. So using this property here, this is really half times gamma of half, but I know that gamma of half is square root of pi. So substituting it square root of pi, I got sigma square root of 2 times half square root of pi, which simplifies to sigma square root of pi over 2. Okay, is that clear? Okay, you could definitely use by parts as well. Okay, any questions from this? Any questions? Too easy? You could check your solution using whether this is this answer by using Mathematica as well. Show you. Okay. Again, using integrate function, you should be able to get the exact answer, which is sigma times square root of pi over 2. And also you can use numerical approximation using n integrate, which is really using Riemann sums for this part. That's 1.25. Actually, you could use this approximation is Yeah, I've used sigma as 1 in this case. Okay. The other method is like if you want to evaluate the sum, okay, using Riemann sum. This is the code that I've used. With that, the small difference is 0.01, okay, for the Riemann sums, which is also 1.5331. Okay. So 3 methods I've explained. You could compute it using by hand by this formula. You could check your answer using the exact value, compute the exact value using Mathematica integrate function, or you could use the approximate value using an integrate function. Okay, that's the expected value. And then the next question is show that the mean, again, show that the variance of x, actually this should be, okay, show that the variance is this expression. Okay, remember how we computed variance the last week? Let me show you. From last week, we know that variance of a random variable is given by its second moment, expected value of x squared minus mu x squared. That mu is the mean squared. So expected value of x squared is the second moment, which you should be able to find using integration again, where fx is the PDF again. Okay, so first thing is you should evaluate this integral. Okay. How would you do that? Okay, that's what you need to compute first. Which method are you going to use? Yeah, she says by parts and maybe substitution. Yeah, you could try that. For this one, it took me a little bit long calculation, and some of the calculations are very messy. But let me explain. The first thing I did was I've realized that every time I use by parts, something like this come across. Okay. This integration come across. So what I did was I did compute what is this integration. So x equal minus bx squared dx. So b could be a constant. And then I got this as minus 1 over 2b equal minus bx squared. So every time this type of integration comes, I use that. So starting with expected value of x squared, which is integral of 0 to infinity x squared fx. Then I said this is using integration by parts formula. So started with by parts, where u is x squared, and then dv is the integral, dv is x over sigma squared e to the power -2 minus x squared divided by 2 sigma squared. Okay, that's the u, that's the u times v part. This is u times v part, and then this is the rest is integral of v du part. Okay. Then simplifying this, I got up to this step where I needed to again use that other integral that I showed you, and the first part, this part is 0, and then what is remaining is 2 integral of x e to the power minus x squared 2 sigma squared dx. Again, this part simplifies to minus 2 0 minus 2 sigma squared times 1. Okay. All right.
Share the other screen. We cannot see that the working.
Oh, really?
Yeah. Thank you.
Thank you. Let me show you. Okay, let me explain again. So variance is expected value of x squared minus mu x squared. Expected value of x squared is the second moment, which is integral of 0 to infinity x squared of the x squared times the PDF of x. Okay, that I computed separately and using integration by parts first of all. So integration by parts formula is here. Just every time I compute this, I noticed that I had to compute an integral of this form. So I did compute integral of x e to the power minus bx squared first. B can be a constant, which gives me minus 1 over 2b e to the power minus bx squared. And using that, okay, integration by parts, this part is u v, the first part, and minus v integral of v du. That's the next part. And simplifying, taking the limit is x goes to infinity. That part is 0. And again, I need to evaluate the second integral, which gives me 2 minus 2 sigma squared half e to the power minus x squared over 2 sigma squared, and then taking the limit of x is x goes to infinity and subbing 0 for the rest. I get 2 sigma squared. That is the second moment here. Okay. So to compute the variance, I also need, this is the expected value. So this part is the expected value of x squared, and minus mu squared. Okay, mu we did compute previously in the previous question, which is sigma square root of pi over 2, and simplifying this part is sigma squared 4 minus pi divided by 2. Okay, so that's the variance. I will tidy this up and then provide full solution once I update the notebook. Okay, any questions? Okay. Moving on to the next question, which is, so that's question 5. Again, you can check your working. This is the working of checking the second moment using the integrate function from Mathematica, which also gives me 2 sigma squared. And then also you can compute this using numerical approximation for the integration using n integrate. So I am explaining all this because you could check your work when you do your assignment. And the same thing, the approximation, you could use Riemann sums to get the approximation. Okay, so variance is simplified is what I have shown previously, which is sigma squared 4 times 4 minus pi divided by 2. Okay, so basically question 1 of your assignment, you should be using similar concepts. Okay, the second part is question 5, helping you to do question 5 of your assignment, simple linear regression problem, which we discussed in assignment 1 as well. When you did assignment 1, you were computing sum of squares. That is like simulation. Okay, but this time you are asked to use gradient descent. But to do that, first of all, you need to compute the expression for gradient of the loss function. The loss function is here. So it's the sum of each observed point minus the modeled value and square the difference. Okay. What would be the gradient? How would you compute the gradient of the loss function? The loss function has 2 variables, beta 0 and beta 1. Okay, how would you compute the gradient? Yeah, Ashish, you're right. Partial derivatives. Okay, so you start with computing the partial derivative with respect to beta 0 first, and then, or otherwise beta 1 first. Take partial derivatives first of all. Okay, let me show you. Okay. We did I think I did explain the concept of linear regression. So you have a least square line, which is suppose you have scatter points, which you think could be modeled using a linear, using a simple linear line. Okay, which has b0 plus b1 times x. B0 is the y-intercept, and b1 is the slope of the line. So the problem here is, by the way, y is called the independent variable and x is called the dependent variable. Suppose you have some points given and then you plot the points, and then every time you draw a line through one of the point, okay, you see that there are some points above and below the line. So the difference between those points and with the line are called errors. So the aim of linear regression is to find which beta 0 and beta 1 gives you the line which gives you the minimum error. Okay, that function is called the loss function. Okay, now you can previously you have used simulation to do this, but this time you would use a gradient descent algorithm for that. The step one in this algorithm is you would let beta 0 and beta 1 be usually initial points. You could choose the initial values to be 0 if you want, and let gamma be a learning rate. It could be a small value, say like 0.001 or 0.01. So you could change this value. Okay, learning rate gives the rate of the speed where the gradient moves during the descent. So for example, if your curve is something like this, okay, take a point and go this direction, and then until you get the minimum, okay? So that's the concept. And setting the learning rate too high would mean invisible paths, or setting it too low might give you slow convergence. Okay, the next step is to compute the partial derivative of the loss function with respect to beta 0 and beta 1. Ideally, you could just use the concept of sum of the derivative of the sum is the sum of the derivative. That if you apply that concept, you could get this is so that would be, just ignore this part. Okay, just ignore this part and ignore this part. Let's say from here, d beta 1 is equal to d by d beta 1 sum of yi's minus beta 0 minus beta 1 xi squared. I goes from 1 to infinity. That's equal to the sum I equals 1 to n d by d beta, sorry, d by d beta 1 of yi minus beta 0 beta 1 xi squared. That's sum of you could use the chain rule here. So that's 2 times this whole thing, yi minus beta 0 minus beta 1 xi multiplied by, this is multiplication, multiplied by the derivative of what's inside with respect to beta 1. So it's minus xi. That simplifies to 2. Okay, minus 2. I goes from 1 to n. xi, yi minus beta 0 minus beta 1 xi. Okay, so that's the derivative with respect to beta 1. Now compute the derivative with respect to beta 0. Which is d beta 0 of the sum yi minus again, using this concept here, that's equal to by d beta 0 minus beta 0 minus beta 1 xi squared. Okay, which is equal to the sum with now this time with respect to beta 0. Times minus 1. Okay, did I get that? Sorry, I missed the 2. So minus 2. Okay, that's the second step. The third step is you would update the current values of beta 0 and beta 1 using these two equations, where beta 1 is your original beta 1, the previous beta 1 minus learning